To apply some useful mechanistic strategies, let's turn our attention to an example mechanism. Under acidic conditions, the cyclic epoxide starting material you see here rearranges to form a dihydropyran product. When thinking about how to start a mechanism, it's nearly always best to consider the nature of the reagents used, the compounds written over or under the arrow. In this case, acetic acid is the reagent that causes the reaction to proceed. Without it, the reaction wouldn't occur, so it makes sense to use it early on in the mechanism. In fact, the acidic conditions suggest that proton transfer to the substrate is a likely first step. But before diving in, let's compare the structures of the starting material and product with the aim of identifying key changes as the reaction proceeds. The enone and geminal dimethyl groups appear to remain unchanged throughout the mechanism. Among bonds that must form, we can identify the aldehyde CO double bond, the CC double bond, and a single bond between the dimethylated and monomethylated carbons. Bonds that appear to break are both bonds from the monomethylated carbon to the epoxide ring and the bond from the dimethylated carbon to the enone portion. To further clarify the situation, let's map atoms in the starting materials and products. Atom mapping will allow you to use concrete statements as you're solving a mechanism and generate a table of bonds made and broken. Here, atoms 1, 2, 5, and 6 are identifiable in both the starting material and products because they're connected to conserved structures. Take a moment to determine how the numbering of the product reflects the bonds made and broken that we just identified. You should notice that carbons 3 and 2 have seemed to switch places, the epoxide has opened and its oxygen has become the aldehyde oxygen, and oxygen 7 remains untouched except for a shift in space. All in all, we can generate this bonds made and broken table. Notice how the red bonds in the starting material and pink bonds in the product match up with the entries of this table. Very often, a bonds table will provide some mechanistic insight. For instance, in this case, we can see that C1 loses a bond to C3 and forms a bond to an adjacent carbon, C2. Both of these operations could be completed in one fell swoop via a 1,2-R step. In the next webcast, we'll carry through this thought process to complete the mechanism.